Okay, so let me go back to the PowerPoint here. And let me erase everything here. Okay, so this question says, hold on 1 minute. Okay, so this question says calculate the pH of the buffer combination of 0.30 m ammonia with 0.36 m ammonium chloride buffer. And then it says, what is the pH after the addition of 20 mils of 0.05 m sodium hydroxide to 80 mils of the buffer solution? So I hope I'll have enough space to do this problem. In fact, let me just show you how to answer the first part, which is very easy. So this is the equilibrium, which is relevant to this particular question. And basically what we need to do is find the pH using the Henderson-Hasselbalch equation that you have been introduced to last time. Just to remind you, the equation says that the pH is equal to pKa of the weak acid involved plus the log of the conjugate base, or the base part of the buffer, divided by the concentration of the acid part of the buffer, which in this case would be the NH4+. So all you have to do is put the numbers in. Now the pKa value would not be given, but if you look in the tables that I provided for you, you'll see that the Ka value or the Kb value for ammonia, write it here, Kb for ammonia, if I remember correctly, is 1.8 times 10 to the minus 5, right? Now, what we need is the pKa. So if you remember, we said that the Kb times Ka would be equal to Kw, which is 1.0 times 10 to the minus 14. Now, another way of stating this is that pKb plus pKa is equal to 14.00. So if you want to find pKa, that would be equal to 14.00 minus pKb, which would be equal to 14.00 minus log of 1.8 times 10 to the minus 5. So if you were to do this calculation, (1.8 times 10 to the minus 5), and if I were to find a minus log of that, that would be 4.74, and then I'm going to subtract that from 14, and that would be equal to 9.2. Well, according to my calculation here, that would be equal to 9.26. Now, I have 9.25 here, but I got 9.26 when I actually did the calculation. So just keep that in mind. So that's a pKa value that we're going to use here, since I have it here already, the 9.26, all right? Okay, so we plug the numbers in. And unfortunately, let me erase this here so that you can see more clearly. Is it okay for me to clear this? Okay, let me erase that. Okay, so you plug the numbers in, and we put the concentration of ammonia here, the concentration of ammonium down here, and then we do the number crunching, and it turns out that the pH of the buffer solution in this case is 9.17 before you added the sodium hydroxide to it, all right? So that's the first part. That's the answer to the first part of the question. Now for the second part of the question, it says, what is the pH of the buffer after adding 20.0 mils of the 0.050 m sodium hydroxide solution to 80 mils of the buffer solution? All right, so I'm definitely going to need some more space for this. So let me backtrack a bit. So the first thing we have to ask ourselves is, what would be the number of moles of the base added? They gave you the volume, which is 20.0 mils, and they gave you the molarity, which is 0.050 m sodium hydroxide. So therefore, the number of moles of sodium hydroxide, hold on. Okay, so the number of moles of sodium hydroxide would be equal to the volume multiplied by the molarity. Now, of course, you have to convert the volume to liters because it's expressed in milliliters. And then we multiply that by the molarity, which is 0.050 M. So let me see what that gives. And again, please do the calculations along with me because I'm not perfect. Sometimes I like to believe I am, but I know I'm not. So make sure that you do these calculations so we're all on the same page in terms of the accuracy of the result. Okay, so that's the first thing we need to determine, the number of moles of the sodium hydroxide added. Oh, I made a mistake. It should be 0.010 moles. All right, so that's the moles of sodium hydroxide. So the next thing I'm going to do now is ask myself the question, okay, so if I'm adding sodium hydroxide to this solution, what will the sodium hydroxide react with, right? So obviously the sodium hydroxide is basic, so that means it's going to react with the acidic part of the buffer, which would be the ammonium, right? So let me see. Oh, another thing I need to do is calculate, before I even do that, is calculate the number of moles of the ammonia. And according to the question, the volume of the buffer solution is 80.0 mils. Again, we have to convert that to liters. 1 liter over 1,000 mils. And then multiply by the molarity, which is 0.30 M. Let's see what that gives. 80 divided by 1,000 times 0.3. So according to my calculations, 0.024 moles would be the result. And then in the case of the ammonium, the volume is still 80.0 mils because they're both in the same solution. Again, we convert that to liters. And then this time we multiply by the molarity of the ammonium, which is 0.36 M. So let's see what that gives. 80 divided by 1,000 times 0.36. So according to my calculations, rounded off to 2 sig figs, that would be 0.029. 0.029 moles, all right? Okay, so we needed to determine the moles of each of these first before we look at what happens next, which is, as I was saying earlier, we need to determine what the added sodium hydroxide will react with, right? It's basic, the sodium hydroxide that is, so therefore it's going to react with the acidic part of the buffer, which would be the ammonium. So next thing I would do is write down the equation for the reaction between the sodium hydroxide and the ammonium. And the result of that will be ammonia plus H2O plus Na plus. All right. Now, in this case, what I would do is write down the ice table, start an ice table, where the initial moles of sodium hydroxide, which is 0.010 moles, and the moles of ammonium, which is 0.029 moles, are written down, and the number of moles of ammonia would be 0.024 moles. We don't need to concern ourselves with the latter two. So as you'll notice, the nature of the arrow that is written here indicates that the reaction is not an equilibrium reaction. So whenever you have a strong base or a strong acid involved in a reaction of this type, it doesn't go to equilibrium. It just goes in one direction until the limiting reactant is used up. Speaking of limiting reactants, based on the first line here, the initial values in this line right here, my question to you is, which of these two, the sodium hydroxide or the ammonium, is the limiting reactant? Let me try that again. 20 divided by 1,000 times 0.05. Yes, you're absolutely right. So thank you for pointing that out. Let me erase this here. So let me erase that here, which means I need to erase that here as well. So this should be 0.0010 moles, and the same thing should be 0.0010 moles. Okay, thank you. So again, I ask a question. Of the two, the sodium hydroxide and the ammonium in the first line, in the initial line of the ice table here, which of those two would be the limiting reactant? In other words, which of those two would be the reactant that would be completely used up? And this is made easier by the fact that the reaction between the sodium hydroxide and the ammonium is a 1-to-1 mole ratio. So which of those two would you expect to be the limiting reactant? The sodium hydroxide. So what does that mean? That means that in the next line, which represents the changes that will take place, all of the sodium hydroxide would be used up. All right? And basically, because of the 1-to-1 ratio between the sodium hydroxide and the ammonium, the change here would be the same, 0.0010 moles. And then on this side, the change for the ammonium would be plus 0.0010 moles, all right? So by the time we get to the end of the reaction, there will be no sodium hydroxide left behind. As far as the ammonium is concerned, the amount that would be remaining would be 0.028 moles. And as far as the ammonium is concerned, the amount that would remain would be 0.025 moles, all right? And then the next step is where we find the concentration of the ammonium and the ammonia. So let's start off with the ammonium first. The concentration of the ammonium would be 0.028 moles divided by the volume. Now, what's the volume? The volume results from adding 20 mils of the sodium hydroxide and being added to 80 mils of the buffer solution. So what does that mean? That means that the volume would be 80 plus 20, which is equal to 100 mils. So you're going to have 100.0 mils here, which you have to convert to liters. 1 liter over 1,000 mils. So let's see what that gives. 0.028. Basically, that's divided by 0.1. So according to my calculation, this works out to be 0.28 M. And then now, as far as the concentration of the ammonia is concerned, that would be equal to the moles that we calculated here, which is 0.025 moles, divided by, again, the same volume. I'm just going to put 0.100 liters. And according to my calculation, that works out to be equal to 0.25 M. Excuse me. Okay, so now that we have the concentrations of both sodium hydroxide, both ammonium and ammonia, then we can plug those values into the same Henderson-Hasselbalch equation. I'm going to need some more space, so I'm going to erase the top part right here. All right, I think that's enough. Okay, so just to remind you of what the Henderson-Hasselbalch equation says, it says that pH of the buffer is equal to pKa plus log of the concentration of the ammonia divided by the concentration of the ammonium. So the pKa, if I remember correctly, was 9.25, right? From the first part, right? So 9.25 plus log of the concentration of the ammonia, which is 0.25 M, divided by the concentration of the ammonium, which is 0.28 M. So let's do that calculation. So we have 0.25 divided by 0.28. Find the log of that, and then add that to 9.25. And the result I got is 9.20. All right? So this is the pH of the buffer after adding that much sodium hydroxide. And if you compare that to the previous pH before you add, if I remember correctly, the previous pH in answer to the first part was 9.17, right? That was before you add your base. After you add your base, it's 9.20, right? So that's a difference of 0.03 pH units. Not much of a difference, all right? And that's basically demonstrating how the buffer works, all right? If you added sodium hydroxide to pretty much any other solution, you will not see that small a pH change, all right? So that's basically how the buffer works. Any questions? Any questions about this? Any questions? Any questions out there in Zoom? Going once? Going twice? Okay, let me continue. Just skip all this here. Okay, so this is an example of the importance of buffer solutions in biological systems. So what is being represented here, and I'm quite sure in your biology courses you've probably met this before. What is being represented here, this red sphere here represents a red blood cell, also known as an erythrocyte. And here it is represented as being flowing through a capillary, a blood capillary. And then, of course, outside of the red blood cell, you have the plasma. And this here represents the tissues. And of course, you know what happens when a red blood cell is transported to tissues. Basically, it delivers oxygen to the tissues and absorbs carbon dioxide from the tissues, right? So this is what happens at the tissues. Now, the actual buffer system would be represented by right here, right? The carbonic acid in equilibrium with the bicarbonate ion, all right? So that's the buffer system right there. So what happens is that the carbon dioxide will move from the tissues into the red blood cell. When the carbon dioxide does that, it basically dissolves in water to form carbonic acid. And then you have the dissociation of the carbonic acid to form H+ ions and the bicarbonate ions, right? The next step, because oxygen is being delivered to the tissues, is that the concentration of H+ will be decreased because the H+ will be needed to react with the oxygenated hemoglobin molecule to form this, which eventually results in the release of oxygen to the tissues, all right? So basically, as this reaction is taking place, this facilitates the forward reaction from the carbonic acid to the bicarbonate ion. You can understand that in the light of Le Chatelier's principle. When the concentration of H+ is reduced, the equilibrium will shift that way, which would mean that more carbon dioxide will be absorbed from the tissues into the red blood cells, all right? So that's what happens when you have the red blood cells being delivered to the tissues. Now, here, it's the reverse, where the red blood cells are in the vessels in the lungs, all right? So in that case, oxygen will be delivered from the lungs to the red blood cells, which reacts with the hemoglobin molecule, which releases a hydrogen ion, and that hydrogen ion will react with the bicarbonate to form the carbonic acid. So again, this is the buffer system right here. So basically, as the concentration of H+ increases, the equilibrium will shift to the left, which further facilitate the release of carbon dioxide in the lungs, and therefore we exhale the carbon dioxide. So this is just one example of how buffer works in biological systems. Okay, titration. So this is something that I'm quite sure if you're in my lab or if you were in my lab before, we have done some titrations in General Chemistry 1. If I remember correctly, we did the vinegar titration, and did we do the hardness of water experiment? Okay, so yeah, we did 2 titrations last semester in General Chemistry 1. So if you have not done that in your General Chemistry 1 lab, let me just briefly describe what titration is all about. So basically, as stated here, a titration occurs when you take a solution whose concentration is accurately known, and then you add it to another solution whose concentration is not known until you add the right amount of one reactant to the other so that they're stoichiometrically equivalent in the reaction solution. And then based on the amounts of the solutions used and the concentration of the known solution, you can determine the concentration of the other solution. The point at which the reaction is complete, where the two reactants are stoichiometrically equivalent, we call that the equivalence point, right? And we add an indicator which changes color at or near the equivalence point so that you know that's the equivalence point that you're reached, and therefore you don't need to add any more of the particular reactant to the other one, all right? So the titration that we did in General Chemistry 1 in my lab course is involving an acid-base titration. And this is kind of demonstrated here, where you have your acid solution present in the flask. In the burette, I don't know if you're familiar with that piece of glassware. The burette is basically a long cylindrical piece of glassware. Let me see if I can find one online so you can see what it looks like if you have not met it before. So let me... And by the way, there's an American way of spelling burette, and then there's the rest of the English word spelling burette. When I was in Jamaica, this is how burette is spelled, with a T. What's that? Yeah, more than likely those are probably British companies. Yeah, so, but anyway, let me see if I can find a good, okay, maybe I should try this one here. Oh, I didn't know that Amazon was in the business of selling beers. Man, they're into everything. All right. Okay, so this is, but I can't show. Okay, let me try another. Let me try another pick. In fact, let me go images. And let me see. Okay, can I see a larger picture? Anyway, okay, let me use this. Okay, so as you can see, burettes come in different sizes. Why do I have to go through all this crap? Okay, so they come in different sizes. I'm trying to find a larger picture. Okay, this will have to do. All right. Yeah, they come in different sizes, right? The largest one I've seen is 100 mil. The smallest one I've seen is the 10 mils. I don't know if there are any smaller, but the way these are designed is that they basically, if you were to see the marks etched on the stem here, you see that it starts with 0 at the top, and then it goes down to whatever the size is, right? So in this case, you have 100 mils down here. In this case, you'd have 50 mils and so on. So the way these are designed, they're designed to measure the amount of liquid that is dispensed from it, right? So it's not a matter of you pouring the liquid into the burette and then you read and then you can tell the volume, right? What you do is take the initial volume, as I'm quite sure Miss Erin can tell you. You take the initial volume reading and then you let out a few mils, and then you take the final volume reading, and the difference between the two would give you the amount of solution that was delivered into whatever flask or beaker that you might have underneath it. So that's a piece of glassware that you'll be using, going back to the PowerPoint here. That's a piece of glassware that you'll be using in this experiment here. Unfortunately, they did not show you the whole picture, right? So in this particular case, the burette will contain a sodium hydroxide, and then you're going to have your acid solution here. You're going to add your indicator. Now, the indicator that we used in our acid-base titration is called phenolphthalein. it's a substance which is colorless in acid, but pink in base, right? So what you do is that you'd add a couple of drops of your indicator to your solution in the flask, which is acidic. So therefore, after adding the indicator, the solution will remain acidic. And then you deliver your base from the burette into your acid solution, and you continue to swirl it until the solution becomes pink. At that point, you turn off the burette, you record the amount of sodium hydroxide or whatever the base is that was delivered into it, and that's basically all you need to do. And then you do your calculations to determine the concentration of either the acid or base, depending on which one you're trying to find. All right, so this shows you what happens in the end. As you may or may not be able to see, that's a light pink color that indicates that you have reached the equivalence point, right? So that's the role of the indicator when it comes to this sort of titration. And I'm not sure if you're going to do this again in the Chem 2 lab. For those of you enrolled in my lab, I'll have to look at the schedule and see. But anyway, that's basically what occurs in titration. Now, the reason why I'm going through all that is because we can plot what are known as pH titration curves, all right? And in this case, this is a plot of the pH on the y-axis versus the volume of sodium hydroxide being added, right? So if you think about the setup I just described, you're going to have your solution, which is acidic, in the flask below the burette, right? Now, an additional part of this particular experimental setup would be that you would put a pH meter probe into the solution to measure the pH at the instant that you're adding your base, right? So that's basically the plot that will result, as you can see here. Now, this is for, and I just realized that the top part is cut off because of this thing which I forgot to remove. Right. This is the titration of a strong acid, strong base situation, right? So your strong acid is in the flask and the base is in the burette, right? So what you're going to do is start off with, before you add any base, what the pH is. In this case, if I'm not mistaken, this is a 0.1 molar, hold on 1 minute. Yes, it's a 0.1 molar solution of acid that you're using, all right? So if you find the pH of the 0.1 molar solution of acid, before you add anything, the pH will be 1, right? And then you start adding your base and the pH will increase slightly until you get to the equivalence point. Now, let me just also say that the molarity of the acid will be 0.1 m and the molarity of the base will be 0.1 m as well, right? So we're assuming that the molarities of both the acid and base are the same. So basically, when you get to the equivalence point, where the amount of acid being added would be stoichiometrically equal to the amount of base, then you're going to have a situation where the pH is 7, right? And that's because the strong acid will completely neutralize the strong base, right? If you remember what happens, for example, if you're reacting, let me do it here, sodium hydroxide plus HCl. This is a strong base, strong acid, and the products of this reaction will be sodium chloride plus water. Remember, we said that if you have a strong base reacting with a strong acid, then the resulting salt would have a pH of 7. In other words, the sodium chloride will not in any way affect water to change the pH, right? So that's why you see here at the equivalence point, in this particular case, the pH is 7. And then if you continue to add more base, what happens? The pH would increase because now you're making the solution more basic, and that continues as you can see here, right? And this is just basically showing you the data that was collected for this particular setup, all right? So that's what happens. This is a titration curve for the reaction between a strong base and a strong acid. Now, if you understand this, then you should appreciate what will happen. Let me just get rid of this here. In the case of a titration between a weak acid and a strong base, all right? So for example, let's say the weak acid is acetic acid and the strong base is sodium hydroxide. So it's the same setup. The only difference is that instead of hydrochloric acid in the burette, it will be the acetic acid in the burette, right? And then you start, well, before you start adding any of the base, you measure the pH of the acid, and the pH would be higher compared to a strong acid because acetic acid is a weak acid. So in the case of acetic acid, the pH is about 3 to begin with before you add anything. And then you add your base, and you have the pH gradually increasing until you get to the equivalence point. But please note here that the equivalence point here will have a pH which is above 7, right? So unlike in the case of the strong acid, strong base titration, where at the equivalence point, the pH is 7, in the case of a weak acid, strong base titration, the pH will be above 7. And again, this is something you should understand as to the reason why, based on what we talked about earlier. Because here is a reaction right here between the weak acid, which is acetic acid, and sodium hydroxide, which is a strong base. The salt that is produced is sodium acetate, and it turns out that the sodium acetate itself will form the acetate ion in solution, and that acetate ion in solution will, no, there's a, hold on, something is not quite, oh, okay, this is the equation I'm looking for. The acetate ion in the solution will react with water to form hydroxide ions and acetic acid. So the formation of the hydroxide ion will make the solution basic, and therefore the pH at the equivalence point, where you only have acetate ions being formed, will be above 7. So that's why you see here the pH is above 7. By my estimation, this looks like 8.72, right? That's the pH at the equivalence point, right? So whenever you have the titration between a weak acid and a strong base, at the equivalence point, the pH would be greater than 7. And then when you continue to add more base, the solution becomes more basic, and therefore the pH continue to increase, all right? Okay, so that's what happens in the case of a weak acid, strong base titration. This is showing you what happens in the case of a strong acid, weak base titration. Now, the strong acid would be hydrochloric acid in this case, and the weak base would be ammonia, and they will react to give ammonium chloride. So as you can see, the titration curve is switched a bit, and the reason for that is that for some reason, whoever put this together decided to do the titration such that the hydrochloric acid is in the burette and the sodium hydroxide is in a flask. Don't know why, but that's how they do it, right? In any case, since the sodium hydroxide is in a flask, that means that the pH will be very high. And then as you add your acid, the pH will fall until you get to the equivalence point. And you'll notice that the equivalence point is less than 7. Why is that so? Well, you have to think about what happens to the ammonium chloride when it dissolves in water. It forms the ammonium ion, which will react with water to form ammonia, and more importantly, H+. So because the hydrogen ion is produced in this case, then the solution resulting at the equivalence point will have a pH below 7. So that's why the pH at the equivalence point in this case is 5.28, which is definitely below 7. And then as you continue to add more acid, the pH basically decreases accordingly, all right? So that's what happens in the case of a strong acid, weak base titration. Okay, so you might be wondering what would be the shape of a titration curve if the acid and base are both weak. Well, in that case, let me get out of this here. And please forgive me for my lack of artistic skills, but I'm going to try to draw what the curve would look like. So again, the y-axis represents a pH, and the x-axis represents, I'm going to say, the volume of base added. All right. So basically, let's say that this is 7 right here, right? Then in the case of a weak acid versus weak base, then what's going to happen is that before you add any base, the pH will be relatively high, below 7, but relatively high. So I'm just going to put it here. If it were a strong acid, it would probably be somewhere down here. And then what will happen is that as you're adding your base, the pH will rise until you get to the equivalence point, right? So it won't rise much. Don't need to rise much. It gets to the equivalence point. And then what's going to happen is that, in fact, to be more accurate, it's going to look something like this. And then it's going to increase and then starts increasing slightly again, right? So basically, okay, now where the pH actually, where the equivalence point actually occurs at the pH depends on which one is stronger, right? If the weak acid is stronger, then the change will occur below 7. If the weak base is stronger, then the pH will occur above 7. So therefore, it depends on the comparative magnitudes of Ka for the weak acid and Kb for the weak base, right? If Ka is larger than Kb, then the pH change will occur before 7. If Kb is larger than Ka, then the pH change will occur above 7, right? So that's what happens in the case of a weak acid, weak base titration. All right. Now, let me see here. What I just did again is a qualitative description of the titration curves. You can actually calculate the pH at different points. And I think the next example is dealing with just that. So this question says exactly 100 mils of a 0.10 m nitric acid solution are titrated with a 0.10 m sodium hydroxide solution. What is the pH at the equivalence point? All right. Now, the first thing I recognize here in this question is that the concentrations are the same for both the acetic acid and the sodium, I'm sorry, not acetic acid, the nitrous acid and the sodium hydroxide, all right? So what does that tell me? It tells me that at the equivalence point, the volume of HNO2 will be equal to the volume of sodium hydroxide, which is equal to 100 mils, all right? So that means that the total volume at the equivalence point would be equal to 100 mils plus 100 mils, right? Which would be equal to 200 mils, okay? Now, the next thing I'm going to do is determine the moles of each, which is also very easy because their molarities and volumes are the same. So the moles of the number of moles of HNO2 would be equal to the number of moles of NaOH, which would be equal to 100 mils, convert to liters, so that's 1 liter over 1,000 mils, multiplied by the molarity, which is 0.10 moles, and that would give 100 times 0.1 divided by 1,000. So that'll be equal to 0.010 moles. So let me write that here, 0.010 moles, all right? So that would be the number of moles of both sodium hydroxide and nitrous acid. So let me write down the equation for that reaction, which is this right here. NaNO2 plus H2O. And then I'm going to set up my ice table with the initial amounts of nitrous acid and sodium hydroxide being the same, which is 0.010 moles, 0.010 moles. And you would have none of that, and you don't need to worry about that, right? So this would be 0 here. And then now, the change would be, now in this case, since you have both of them being the same in terms of the number of moles, that means that the change here would be minus 0.010 moles. The change here would be minus 0.010 moles. And as far as the sodium nitrite is concerned, the change will be plus 0.010 moles, right? So at the end of the reaction, there'll be none of this here, and the only thing remaining at this juncture would be the sodium nitrite, 0.010 moles of that, right? So the next step is to find the molarity of the sodium nitrite, which, by the way, is the same thing as the molarity of the nitrite ion, which is what we really need. And that would be equal to 0.010 moles divided by the volume. Now, what's the volume? Remember, we mixed both of them together. So the final volume is what we calculated here, which is 200 mils. I'm going to put that down here, which again, we have to convert to liters. 1 liter over 1,000 mils. All right? And then we work that out. So that would be 0.010 divided by 200, 1,000. So according to my calculations, this works out to be equal to 0.050 M. All right? So that's the molarity of the nitrous acid. Now, we're not finished yet because what the question is asking for is the pH of the solution at this point. And again, I'm going to need some more space. So let me erase the top part here because what we have to look at now is the effect that the nitrite ion will have on the water that it is dissolved in. All right? So we're going to start off with the nitrite ion. We're going to start off with the nitrite ion, and when it is hydrolyzed by the water, you're going to have this equilibrium set up to form HNO2 plus OH minus. So at this juncture, I can tell you, without doing any further calculation, that the pH will be above 7, right? And that's because the hydrolysis of the nitrite ion gives you hydroxide ions, right? So I'm going to set up my ice table here. The concentration of the nitrite is 0.050 initially. We don't need to worry about water. This would be 0, this would be 0. And then the change here would be minus X. We don't know what the amount of nitrite ion that will undergo this reaction, so we're going to call the change X. This would be plus X here for the nitrous acid, and this would be plus X here for the hydroxide. And then at the equilibrium state, you're going to have 0.050 minus X. Here, we're going to have X. Here, we're going to have X. And then, need more space. Okay, so basically what we need to do now is write down an equilibrium expression for this state of affairs here. And because the nitrite ion is acting as a base in this case, it's producing hydroxide ions, we need to write down a Kb expression for this, which is equal to the concentration of HNO2 times the concentration of hydroxide, all divided by the concentration of NO2 minus. And then we put in the different terms. So basically simplified is going to give you X squared over 0.050 minus X. So at this juncture, I have a question for you guys. What would be the next step? What would be the next step? We did something like this before in the case of a weak base. In this case, I'm sorry, in the case of a weak acid. In this case, it's a similar approach, but the only difference is that we're dealing with a weak base, the nitrite ion. So what do you think the next step is? Anybody? Including you guys out there in Zoom, you can chip in with your suggestions. What would be the next step? Well, we make an assumption or an approximation, right? So what would be the assumption? Right, so we assume that X is very small compared to 0.050, which means that 0.050 minus X would be approximately 0.050, right? So what that means is that this is simplified to x squared over 0.050, right? The aim is to determine x, because once we determine x, we can determine the OH minus, and therefore we can determine the pH. So x in this case would be equal to the square root of KB times 0.050, right? Now, here's the thing. The tables that I've provided for you in Canvas does not give you the KB value for nitrous acid. I'm sorry, does not give you the KB value for the nitrite ion, right? In fact, let me see if I can bring up the table here. So let me go to okay. Files, tables. Okay, so we're looking for dissociation constants. Okay, so this is the table that you'll have access to in your future tests, exams, whatever. Okay, so if you look at this table, and if you look among the bases here, you do not see the nitrite ion. However, if you look up top here, you'll see that it does provide the Ka value for nitrous acid, right? And if you recall, going back to the PowerPoint, okay, so going back to the PowerPoint, you have the Kb value here, which you're not given, but you have the Ka value for the corresponding acid. So can anybody remind me of the relationship between the Ka of an acid and the Kb for the conjugate base of that acid? There's a relationship between the two. What's the relationship between the Ka for an acid and the Kb for the conjugate base of that acid? Feel free to look in your notes. Ka times Kb is equal to Kw, which is equal to 1.0 times 10 to the minus 14, right? So therefore, we can express this equation as Kw divided by Ka times 0.050, right? And if we put the numbers in, you're going to get 1.0 times 10 to the minus 14 divided by Ka, which is, I have to go back to the table that I just pulled up. Hold on. So, okay, so the Ka for nitrous acid is 4.5 times 10 to the minus 4, which is pretty high, now that I've looked at it. So it's 4.5 times 10 to the minus 4. So I'm going to put 4.5 times 10 to the minus 4 multiplied by 0.050. Let me go back to black ink. So that means that x would be equal to 1 times 10 to the minus 14 times 0.05 divided by 4.5 times 10 to the minus 4. And then I find the square root of that. So according to my calculations, this works out to be equal to 1.1 times 10 to the minus 6, right? M. And this would be equal to the concentration of OH minus. So now that we have found the concentration of OH minus, now remember again, the aim of this exercise is to determine the pH. So now that we have the concentration of the hydroxide ion, how would you determine the pH based on that? Well, let me give you a little hint. Remember this? What does that equal to? The pH plus the pOH of a solution is equal to what? Always. It's equal to a number. 14.00. So how does that help? Remember now, the aim is to find the pH, right? So how do we find the pH based on this value for the concentration of OH minus? Okay, so 14, do that down here. So pH is equal to 40. pH is equal to 14.00 minus pOH, okay? What next? How do we find the pOH? I'm sorry? Exactly. Minus log of 1.1 times 10 to the minus 6. So whatever that gives, that would be the pH. Let's see what that gives. 1.1 times 10 to the minus 6. Well, minus plus, so plus 12. 1.1 times 10 to the minus 6. Find a log of that, then add that to the 14. And the value that I got is 8.04. Which is above 7, as I predicted. The pH would be above 7 because the hydrolysis of the nitrite ion produces hydroxide ions. All right. Any questions about this particular example? Any questions? Any questions? Okay, in the meantime, let me see if anybody else came in late. Let me see. Oh, Miss Jones decided to join us. So Jones is here. And Jabbar is here. And I think that's it. Yes, ma'am. Oh, what's your last name? Labrador. Yes, you're here as well. All right. Yes, so you say, Miss Jones. You weren't here when I started the class, so anyway. All right. Let me shoot, what am I doing? What am I doing? Let me go back here. Share my screen again. And then bring up the PowerPoint. Okay, so that's how we do that one. Let me see what's next. Okay, so let's talk about indicators. And we mentioned indicators before because we use them to indicate the point of a titration, the equivalence point, right? Now, you cannot just use any old indicator to do that. You have to be specific in terms of the indicator you choose. And the choice of indicator is mainly dependent on what the pH would be at the equivalence point. As you remember, in some cases, the pH would be 7 at the equivalence point. In other cases, it would be either above or below 7. So you have to take that into account when you're doing titrations in terms of choosing the right indicator for an acid-base titration, right? So indicators are basically weak acids and bases, right? And they're special in that let's say you're dealing with a weak acid, such as represented here, right? What you'll find is that the undissociated molecule will have one particular color, and then the conjugate base will have a different color, right? So in the case of the phenolphthalein indicator, the acid form of the indicator would be colorless, but the basic form of the indicator would be pink, right? And what you're looking at here is a list of different indicators and the different colors that they will have in acid or base. And one key thing I want to point out here is that there's a pH range within which there'll be a changeover from one color to another, right? So for example, taking the first one here, thymol blue, it will be red in acid and yellow in base. But what you'll find is that below 1.2, the color will be red, and then between 1.2 to 2.8, the color would be a combination of red and yellow, which would be orange. And then after 2.8, as you increase the pH, the solution or the indicator color would be yellow, right? So that's basically how indicators behave, right? So there's a general rule of thumb that is used to indicate whether or not the solution will take up or take on a particular color of the indicator that predominates, right? And that is this right here. If the concentration of the acid form of the indicator is greater than the conjugate base to this extent, where the ratio is greater than or equal to 10, then the color of the acid form will predominate. Now, if it's reversed, right, where this ratio is less than or equal to 10, then the color of the basic form will predominate. Now, within the 10 ranges on either side, between those two 10 ranges, then the color would be a mixture of the resulting color would be a mixture of the colors of the two forms of the indicator, all right? So that's basically how indicators behave. So as I said before, when it comes to acid-base titration, the choice of indicator is very important, and that is demonstrated in the next question, or in this graph right here. But before I do that, let me just show you this here. This is a picture of a particular compound that is isolated from the leaves of cabbage. And these are different pH. I wish they had put the actual pH values down here. But basically, what you'll find is that as the pH of the particular solution increases, that the pH that the indicator is in, you see the color change, you know, as you can observe right here. All right. So that's just an example of how the color can change according to the pH for these substances. So this graph here illustrates the importance of the choice of indicator that you use for titration. So what you're looking at here is the titration curve for a strong acid and strong base. This is what we saw earlier with respect to the reaction between sodium hydroxide and hydrochloric acid. Now, as far as, so you have three indicators here represented. You have thymol blue, you have methyl red, and you have phenolphthalein, right? Thymol blue changes color within this range, right? So this looks like a pH range from about 1 point something to about 2.5, 6 or something like that. Methyl red changes from red to orange from about 4 point something to about 6 point something. And then phenolphthalein, its color changes from colorless, which is at about just above 8 to about 10, right? Now, if you're going to do a titration using any one of these indicators for indicating the equivalence point, the indicator that you would not choose in this case would be this one right here, right? And the reason why is because when you're adding your base to your acid solution, the color change will occur before you get to the equivalence point. So therefore, it would not serve the function of indicating the equivalence point, right? These two would be better choices, right? Because the pH range for the color change in each of these cases overlap with where the equivalence point is, where you have a jump from a low pH to a high pH, right? So therefore, if you're going to do titration of a strong acid with a strong base, then you would use either phenolphthalein or methyl red if these are available, but you certainly would not be using this indicator, thymol blue, all right? So that's just basically illustrating the importance of the choice of indicators for acid-base titration. So here's a question that is being asked. And it says, which indicators would you use for the titration of nitrous acid with potassium hydroxide? And it gives you these indicators here and their pH ranges, right? So first thing you have to ask yourself is what type of acid we're dealing with here and what type of base we're dealing with here, right? So what type of acid are we dealing with here? Is it a strong acid or a weak acid? Nitrous acid. It's a weak acid, right? And the potassium hydroxide is a Strong or weak base? Is potassium hydroxide a strong or a weak base? What? Hmm? Okay, let's say sometime. It's a strong base, right? So if you're titrating a weak acid with a strong base, what would you expect the pH at the equivalence point to be at 7, above 7, or below 7? Above 7, right? So based on that conclusion, what of these indicators here, which of them would you use in that titration? Yes, in fact, the last one can be used. In fact, I'll choose the last two ones, right? Because the last two ones here, the first one, Cresol Red, has a pH range from 7.2 to 8.8. And then the phenolphthalein is 8.3 to 10.0, right? So you can use either of those two indicators to indicate the equivalence point of this particular titration. What time is it? Oh, okay. All right, so that's as far as that is concerned. Okay, so I'm going to stop here for today, but let me just say that based on what we have covered so far, let me see if I can come on. Find assignment number. Okay. Oh, I did not publish. Did I give you guys assignment number 5? Okay, my bad. So let me open this up and download it. Okay, so this here is assignment number 5, and you should be able to do questions numbers 1. Oh, definitely number 1. Number 2, maybe not yet. In fact, I think I may need to help you guys out with that one. Let me not say number 2, and let me look at number 3. No, you won't be able to do number 3, number 4, number 5. Okay, so the only one so far you should be able to do. Oh, and number 8. Number 8 deals with indicators. You definitely should be able to do number 8. All right, so basically numbers 1 and 8, you should be able to do at this juncture. What I'm going to do next class is look at question number 2, because we did something similar just a while ago in terms of pH at the equivalence point. But question number 2 deals with calculating the pH at different points of the titration curve, right? So we have not done that, or we have not done an example of that. So I'm going to work with you to do number 2, which has a couple of parts. Yeah, so number 2, I'm going to help you out with, and then we're going to move on to solubility product, which is what question number 3 is all about. All right? Okay, so that's it, folks. I'll see you guys on Monday. All right, take care.